So remember we had this Euler-Fermat theorem that was telling us how to compute the number of integers less than a given n that will be relatively prime to that number n. So we had this definition of the Euler phi function. Okay, so p of n, so the set of all a between 1 and n, such that GCD of a and n is equal to 1. An equivalent way of describing that would be the size of z mod n star, right? So since z mod n star is defined just to be precisely this set of integers. Okay. All right, and so also remember a particular case of calculating the Euler phi function that will be important for us is that phi of p times q is going to be p minus 1 times q minus 1 when p is not equal to q, and each of those things are prime numbers. Okay. All right, so now we have a generalization of the Fermat's little theorem. Okay. So this is the Euler-Fermat theorem. And so this says that if a is in z mod n star, then a to the phi of n will be congruent to 1 mod n. Okay. And the reason for this is exactly the same as the reason that Fermat's little theorem is true. And in fact, if p is prime, then phi of p is just equal to p minus 1. So the reason this is true is that, well, phi of n is the size of the group, so we know the order of any elements divides the size of the group. So if we raise a to the power which is the size of the group, then that's going to have to give us 1 back. Okay. And then corollary, so again, if we're working mod n and we want to reduce an exponent, then a to the k will be congruent to a to the k, where k is reduced, or a to the k reduced mod phi of n. Okay, because here the two exponents just differ by a multiple of phi of n, but a to that multiple of phi of n is just going to 1. So that will give you the same expression. Right? So this left-hand side here is also congruent to a to the k reduced mod phi of n plus some n times phi of n, right? But then that whole thing would just be going to 1. Okay. All right, so again, so we're working mod n. We can reduce the exponent and expressions of the form a to the k, provided that the base is invertible mod n. So we're actually working with something in that group, z mod n star. And we do that reduction with respect to the proper modulus, namely phi of n. Okay. All right, so we've got sort of all the number theoretic preliminaries out of the way to be able to describe the RSA cryptosystem. Okay. So before we describe RSA, let's just give a definition of what a cryptosystem is, since this is really the first public key cryptosystem that we're looking at. Okay. All right, so in a cryptosystem, we have a set of allowable messages, also known as plain text. Okay, so I use the sort of script P for that. A set of allowable ciphertext C. Almost always P and C are the same sets. Okay, so anything that's a plain text could be a ciphertext and vice versa. A set of possible keys K. And in public key crypto, that means that keys will have both public and private components. So you have to specify what's the public component of the key, what's the private component of the key. And then functions, E sub k and D sub k, that are going to tell us how to encrypt and decrypt. So we must have that for any plain text data, the decryption of an encryption with the same key has to give me that original plain text back, right? Otherwise, the crypto system is not actually working to correctly decrypt encryptions of messages. Okay. All right, so we're going to describe RSA now. Okay, so we'll assume that Bob is the party that's doing the setup here. So here's what Bob's going to do. So choose primes P and Q, and computes the products of those primes. Okay. Right. And we should note here that so P and Q should both be odd primes, and they should not be equal to each other. So we need to pick two distinct primes here. Plaintext and ciphertext are going to be integers in Z mod n. Okay, so if we want to send a message, and suppose we want to send some meaningful message in some language, some natural language, say English, could be any language though. We're going to have to find some way to encode messages as integers. Okay, and that method will, that'll be completely public, unkeyed, known to anyone. Okay, so we'll just have some agreed upon way to take whatever we want to send and encode it as a single integer. Another thing that may happen is, we may be sending blocks of data. Okay, and so then we would probably just agree upon a block size, encode any block of data in binary, and so then the message would just be the corresponding integer whose binary representation is that string of text. Okay, and we'll talk a little bit about encoding, but for now we're not going to worry about the details of that. So we're just going to assume that we have some way of taking messages, translating them into integers in Z mod n, and now we're going to encrypt integers in Z mod n as other integers in Z mod n. Okay. All right. So again, note that B of n here is going to be P minus 1 times Q minus 1. Okay. All right. So then Bob is going to choose some A that is going to be invertible, but invertible mod phi of n. Okay, so not necessarily invertible mod the original n, but definitely invertible mod phi of n. Okay, and so this A is what's going to be serving as an encryption exponent. Then Bob is going to compute B, where B is going to be the inverse of A mod phi of n. Okay. So this will be the decryption exponent. Okay, so Bob is going to publish N and A. So we've got a public modulus, we've got a public encryption exponent, but keep the primes P and Q, and keep that decryption exponent B secrets. Okay. All right, so then my key is going to consist of the components N, A, and B. Okay. So the public key consists of the components N and A. The private key consists of the component B. Okay, so suppose Alice wants to send a message to Bob. Okay, so Alice is going to encrypt this plaintext message M in Z mod n as a ciphertext, which will be M to the A reduced mod n. Okay. And then C is what Alice is going to send to Bob. Okay, so and then in terms of the parameters of the crypto system that we described above, so E sub k of message M is M to the B reduced mod n. Okay, Bob is going to recover that original message by taking the ciphertext and raising it to the power of the private decryption exponent. Okay, so another way to say that then, D sub k, so decryption with this key of ciphertext C is C to the B mod n. Okay. All right, so why does this work? Okay, well, we need to verify this property, right? That's decryption of encryption with the same key is actually going to give me the original message back. Okay, well, encryption is M to the A. Okay, decryption of that, so even though it's the same key, the key has public and private components, and we would be using the private component as the decryption exponent, so that'll be the B. So this will be M to the A to the B mod N. Okay. Which is just M to the AB mod N. Okay. But by what we saw above, right, this will be the same if we reduce that exponent, mod phi of n. Okay, but what's A times B reduced mod phi of n? Well, how were A and B chosen? They were chosen to be inverses of each other, mod phi of n. Another way of saying that is A times B is congruent to 1 mod phi of n. Another way of saying that is if I reduce the product of A and B mod phi of n, it reduces to 1. Okay. So this just goes to m to the 1. Okay, but that's just the same as m. Okay. All right, but m was originally a message in z mod n, so it was already normalized. So if it's reduced mod n, that just gives me n back. Okay, so that simple way of showing why decryption of encryption gives me the same thing back. So now there may be a flaw in my above description, so I'll maybe let you think about that a little bit, and then maybe at the end of the class we'll come back and see if maybe there was an issue or an error here. But so far looks okay. All right, so let's look at a small example then. Okay. All right, so I'll take two distinct odd primes. I'm taking a couple very small primes here. So P is equal to 11, Q is equal to 17, so my modulus would be 187. All right, so what's phi of n going to be then? Okay, well, just the product of the phis of those factors, and those are prime, so just p minus 1 times q minus 1, or 160. All right, so suppose then I just at random choose the public encryption exponents to be 39. Okay, so we want to run the extend Euclidean algorithm, and if I do that, I can get 1 as a linear combo of 39 and the modulus 160. Okay, and so it turns out that 39 times 119 minus a product of some integer on my modulus gives me 1. So I can see then that the inverse of 39 mod 160 is 119. Okay, so I should take my decryption exponent to be 119. All right, so Alice wants to send a message, and so suppose her desired message is the capital letter A, and the way she's going to do this is just send the ASCII code. Okay, so we talked about you have to come up with some way of encoding messages if you want to send them. So we're going to suppose that the encoding of the letter A is just the integer 65. Okay, so my plain text would be 65 then. The ciphertext would be 65 to the public exponents reduced mod the public modulus. Okay, and so if you work that out, you get 142. Bob receives the ciphertext 142, now wants to decrypt. Okay, so the private exponent B was 119. So he computes 142 to the 119, which reduces back to 65. Okay. All right, and I encourage you to just check out these calculations on your own device. Just make sure that everything actually works out there. So we see an example of encryption and decryption and actually giving the same thing back. All right, so here's a few questions about RSA. And this is the point in the class where I usually pause and ask students what questions they have. And, there's always many good questions. So you may want to again just sort of pause and and think about what questions you have about this crypto system. Okay, so a few natural questions here are, well, security is this actually secure? Right. So again, this may be the first example you've seen of a public key crypto system, and well, small examples of any crypto systems are going to be non-secure. But this looks particularly suspicious. So, for example, here, if I see n, if I know the public modulus n, what would I have to do to break the system? Well, I would have to factor n. Right? If I factor n, then I can get v of n. And then once you've got that, everything else here is just done with known very efficient algorithms. Right? So inverting the public exponent to get the private exponent, and then once you have the private exponent, you can decrypt. Okay. So even if we're working, so obviously we would have to bump up to very large moduli to have any chance of having security. But if we do that, how can we be sure? How can we be sure that nobody could actually factor our modulus and break the system that way, or find a different way to break the system? Okay, so those are questions we'll talk about. How does the security depend upon the parameters? So as we just mentioned, we need a very large modulus, so we need very large primes to have security. Is that sufficient, or are there other conditions on how we choose the primes, how we set up the modulus? Should we choose these two primes independently of each other, or are there relationships that should hold in order to have some sort of security? And what about the encryption and decryption exponents? Does it matter how we choose the encryption exponent? Is the resulting decryption exponent, is there going to be any flaw in the security based on that? Okay. So those are all good questions about security that we'll address eventually. How do we get these candidate primes in the first place? Is it enough just to randomly generate numbers of the appropriate size and then test those for primality? That would require, I think this word requires should be under the second point there, but that would require some sort of efficient primality testing. Okay, if I've got a really large number, how do I figure out if it's prime? And we already said that the whole security of this depends upon not being able to factor really large numbers efficiently. So this would require a way to test numbers for primality that wouldn't actually require factoring numbers. And there's no a priori reason to assume that such a thing would even be possible, right? So we need to find some way to test large numbers for primality that doesn't require factoring. And are there enough primes out there, right? If we're just grabbing random numbers and trying to test them for primality, are we ever going to run into an issue where the primes aren't dense enough? So we just keep grabbing numbers, and we keep grabbing numbers that turn out to be composites. Okay. And then another question. This is kind of more prosaic, but what about running RSA itself, right? Can we do this efficiently, right? The example that we looked at, well, the numbers are so small it didn't really matter. But if if I'm trying to raise a number to, say a 1,000-bit exponent with a 1,000-bit modulus, something like that, or probably even bigger, maybe 2,000 bits, am I going to be able to do that exponentiation efficiently? Right? So we know that we've got efficient algorithms for multiplication and division. But exponentiation, well, you run into really big numbers if you do that. So can we do this efficiently? All right. Okay, so let's talk about just that first sort of most basic question before we move on to some of the other questions. Is modular exponentiation even really feasible? Okay. All right. And okay, so here's kind of a wall of text, and I'll let you read this over on your own. So basically, in order to have an efficient algorithm, What we need is we need to be able to, we're going to sort of measure complexity in terms of basic operations, which just means things that we know that we can do efficiently for the size of problem we're dealing with. Okay, so for example, multiplication or division will count as basic operations. And we want to show that sort of no matter the size of our inputs, the number of basic operations that we're going to need to use isn't going to be too bad. Which basically means that ideally the number of basic operations would only grow linearly as we grow the size of that input, or maybe grow according to some other polynomial. Okay. The other thing we have to worry about here is, what do we mean by size of inputs? And so if we're talking about integer inputs, the appropriate measure of that is the log of the number itself, right? Because if we've got say 1,000-bit integer, right, that's a really large number, but we can still represent that on a machine, well, with 1,000 bits. Okay, so we would want to look at a log base 2 of that integer as a measure of the size of the inputs. Okay, so we need our algorithms, their running time to not get too bad as we increase the number of bits in the integer. Okay, so meaning that we could be dealing with very, very large integers because we can represent very large integers using a relatively small number of bits on a machine. Okay, so that's the appropriate way to measure the complexity of the algorithms, that we can still run things efficiently with relatively few basic operations, even as we add bits to the size of our inputs. Okay. So again, I'll let you read over my description here on your own time, but that's sort of the summary. Okay. All right. So can we do exponentiation efficiently? So again, if we've got a very large number b, and I want to calculate m to the b, I don't want to do m times n times n times n b times, right? Because if b is say on the order of 2 to 1,000, then I'm going to be doing on the order of 2 to the 1,000, or roughly 10 to the 300 multiplications. Okay, no way I'm going to be able to do that before the universe ends. Okay, so let's try to find a more efficient way of doing multiplications. All right, so for example, suppose I wanted to calculate 2 to the 64 mod n. And I'm going to assume I have no knowledge of phi of n here. So in a lot of these problems, we could sort of cheat and do things quicker if we knew phi of n, but the person doing the encrypting is not going to know phi of n. So we're just going to assume we have to do this the long way. All right, so what would I do if I wanted to do 2 to the 64, right? Well, again, we could sort of use our naive method that I just described verbally, and just do 2 times 2 times 2 times 2. And so there would be 63 multiplications here. And maybe reduce mod n as I go. But a much better way of doing this would be just to keep squaring, right? Because 64 itself is a power of 2. Okay, so I can do 2, square that to get 2 squared, square again to get 2 to the 4th. Okay. And then just keep squaring. Each squaring is a multiplication, so I can just count the number of arrows here. And so I've got 1, 2, 3, 4, 5, 6. 6 multiplications. What's the relationship between 6 and 64? Well, 2 to the 6th is 64. No idea where I got 26 from. Okay, or 6 is log base 2 of 64. Okay, so in this case, I needed just log base 2 of the power multiplications. Okay. All right, but I'm kind of cheating a little bit there, because 64 is an even power of 2. Right, so 64 is an integer power of 2, is what I should say. Right, so what if I'm dealing with something that is not an integer multiple of 2? Okay. All right, so how could I calculate x to the 83 using few multiplications? All right, now there's sort of two ways I could do this. All right, so one thing I could do is, well, either way, I'm going to want to write 83 in binary. Okay. So what's 83? Looks like it's 64. All right, plus 16 gives me 80 plus 2 plus 1. So binary, so 64 place, 32nd place, 32's place, 8th place, 4's, 2's, and 1's. Okay, so there's 83 in binary. All right, so one thing I could do would be to just do all the squarings that I would need to get up to x to the 64. Okay. And then just go ahead and multiply the corresponding factors. Okay, so I could do x, and again, so just start with x, do all the same squarings as before, et cetera, et cetera. Okay, we already saw on the previous slide that would take 6 multiplications. And then just pick out the factors I need, right? So now x to the 83 is x to the 64 plus 16 plus 2 plus 1. Right? But by the laws of exponents, that's this. Okay, and then these things I all calculated, so that's 3 more multiplications. Okay, and so that's a total of 9 multiplications. Okay. All right, and so compare that to the 82 multiplications you would need to do x to the 83 the naive way. All right, so we're still kind of somehow on the order of log base 2 of 83 here. All right, so that's good. However, one thing that's kind of irritating about this is that you have to do all these squarings and then keep track of the entries you need, and there may be a lot of those. So that may take quite a bit of space and memory, and then you got to pick out the ones you need and multiply all those together again. So sort of a slicker way of doing this. Let me see if I left myself enough room. Okay, so a slicker way of doing this is to do what we'll call left to right binary square and multiply. Okay, so the algorithm we just showed is called square and multiply, and we did it in sort of a right to left way. Okay, so let's do the other way around. So this will be left to right. Okay, so here's what I'm going to do. I'm going to write my binary expansion of my exponent, 83 in this case. All right, and I'm going to start off, and I'm going to think of starting in this column here, and write x to the 1. Okay. And so basically what I'm going to do then is I'm going to shift right, and every time I shift right, I'm going to square what I have. Okay. And so notice there's going to be a total of 1, 2, 3, 4, 5, 6 right shifts here. So this x to the 1 is going to get squared 6 times. And as we saw before, getting squared 6 times is going to leave you with x to the 64. Okay. All right, on the other hand, anytime I see a 1 in a column, I'm going to multiply by x. Okay? And so that's picking up another increment in your exponent, and that increment is going to get squared the correct number of times. Right? So when I get here, I'm going to multiply by x, and so then that's going to get squared 4 times, and that's going to allow me to pick up x to the 16. Okay. All right, so I kind of I kind of start here, and I would sort of think of this as having x to the 0, and then multiplying by that to get x to the 1, which is, and I'm going to sort of have two rows here, and that's why I put this in the bottom row. But I don't want to draw that initial arrow because I don't want to count that as a multiplication, because I'm actually initially starting with x to the 1. Okay. All right. So what I'm going to do then is shift right. Every time I shift right, I'm going to square, so I get x squared. And then if I see a 1, I'm going to multiply by another x. So I don't see a 1 there. Okay, so square, just square to get to the next column. Here I see a 1, so I am going to multiply by x. Okay, so I get x to the 5th. Okay, shift right and square. Okay, I see a 0 here, so I'm not going to multiply by an additional x. I'm just going to shift right and square. Again, I see a 0. So shift right and square. Okay, here I see a 1, so I am going to multiply by an x. So x to the 41. Okay, shift right and square, x to the 82. And here I see a 1. So again, multiply by another x. And so notice I end up with x to the 83. Okay, and again, so the very nice part about doing things this way is the only powers of x you need to keep track of are the current ones that you're computing. Right, so you don't, and then once you're done computing it, you're done with it. You can throw it out, right? So the only things you really need in memory are x and the current power of x. And then, of course, the binary expansion of your exponent that you're going to be shifting through. Okay, so let's quickly here then try to look at a worst case analysis of this method. Okay, so if my exponent then has a bit length of n. We say bit length of k actually, since I'm usually using n for my base. Okay, so it's got a bit length of k. What's the worst case number of multiplications that I would need in this method? Okay, so bit length of, let's call it x to the a. All right, so then I would have k bits in the expansion. And the worst case is that they're all 1s. Okay. And so if I've got k1s, then okay, so every time I shift, I have to square, which counts as a multiplication. All right. If I have a 1 in each column, every time I see a 1 past that first one, I'll have to multiply by x. Okay, so this would then require k minus 1 squarings and k minus 1 multiplications by x. So 2 times k minus 1 total multiplications. Okay. All right, but if the bit length of a is k, that means that k is going to be approximately log base 2 of a. All right, and all right, so then that means that this, right, will be approximately 2 times log base 2 of a. Okay, but so that's great news, right? So that's telling us that, at least in terms of the number of multiplications we need, that this left to right binary square multiply algorithm is linear in the log of the exponent. Okay, so linear in the bit length of the exponent. So that means we could scale these exponents up to several thousand bits without having any problems, at least in terms of the number of multiplications that we need to do exponentiation. Okay, but now we would also have to worry about the number of reductions, and and making sure that the numbers we're actually working with don't blow up. Okay, so we'll see how to deal with that in one of our in-class sessions. Okay. All right, so that's it for this class. Talk about other implementations of RSA or other issues of RSA implementations in our next few videos.